Welcome back. Today we're moving from the high-level concepts of network architecture and diving straight into the foundation of it all, the physical layer. In Day 03 of our series, we're focusing on cabling and speed. Think of this as the literal nerves and veins of the digital world. We'll be breaking down the essential media that makes communication possible. Our agenda covers the heavy hitters of modern connectivity. We'll compare the reliability of copper, specifically Cat6 and 6a, against the lightning-fast capabilities of single-mode and multi-mode fiber. We'll explore the rise of multi-gigabit, or mGig ports, pushing boundaries at 2.5, 5, and 10 gigs. And finally, we'll look at PoE++, the standard powering the next generation of high-demand IoT devices. Now that we've established the importance of the physical layer, let's talk about the most common way we interact with it: Ethernet. In a world where gigabit fiber plans are becoming the standard, your physical cable is either a wide-open pipeline or a frustrating bottleneck. It doesn't matter how fast your ISP is if your cable can't handle the load. As you can see on the slide, we're going to be decoding the various categories, from Cat 5 and 6 all the way up to Cat 7 and 8. Choosing the right LAN cable is about more than just a connection. It's about matching the right hardware to your specific home or office needs. We're going to cut through the marketing jargon and technical specs to help you find that perfect match for your router and devices. Let's break down the sweet spots and the future-proof options. Let's start at the very beginning of the Ethernet family tree with the entry-level cables, Cat 5 and Cat 5e. If you find a cable labeled simply as Cat 5 in your storage bin, my best advice is to recycle it. With a maximum speed of just 100 megabits per second, it is officially obsolete. In today's world of high-speed streaming and large file transfers, it's a major bottleneck. Next, we have Cat 5e, or Enhanced. This is the minimum standard for a modern home. While it can technically handle speeds up to 1 gigabit per second, it's really intended for basic web browsing, or those standard cables often bundled with your ISP's router. Think of Cat 5e as the absolute baseline for 2026 gigabit connections. It gets the job done for the basics, but it doesn't leave much room for growth. Now we're entering what I like to call the sweet spot for modern networking, Category 6 cabling. If you look at the cross-section on the slide, you'll see a major physical upgrade. That plastic core in the middle is called the spline, or separator. Its job is simple but critical. It keeps the wire pairs separated to drastically reduce crosstalk and electrical noise. This physical change allows for much higher performance. While 1 gigabit per second is the standard, Cat 6 can actually push up to 10 gigabits per second over shorter distances of up to 50 meters. With a bandwidth of 250 megahertz, it handles data much more efficiently than the older 5e standard. This makes Cat 6 the ideal choice for high-demand tasks like 4K streaming, stable Zoom calls, and lag-free console gaming. If you're a gamer or a professional working from home, this is the reliable backbone you want for your local network. But what happens when you need that 10 gigabit speed to stay consistent over much longer distances? That's where Cat6a comes in. The A stands for augmented. As you can see in the comparison image, Cat6a features thicker insulation and tighter twists in the wire pairs. This physical bulk makes the cable more rigid, but it serves a vital purpose. Unlike standard Cat6, which can drop in speed over distance, Cat6a delivers a consistent 10 gigabits per second, up to the full 100-meter limit. With a doubled bandwidth of 500 to 600 megahertz, it's a powerhouse for data-heavy environments. Because it's a bit harder to work with due to its thickness, we recommend this as the go-to choice for internal wiring in major renovations. If you're pulling cable through walls today, Cat6a ensures you won't have to do it again for a very long time. As you can see in the diagrams, most home cables are UTP, or unshielded twisted pair, which is perfectly safe for standard environments. Cat 7, on the other hand, is almost always STP shielded twisted pair. Here is the risk. Shielded cables require proper earthing or grounding. If your home electrical system isn't perfectly grounded, that metal shield doesn't block interference. It actually acts like an antenna. Instead of a cleaner signal, it attracts radio frequency interference, which can result in worse performance than a much cheaper Cat 6 cable. Unless you are working in a specialized industrial environment with guaranteed grounding, Cat 7 is often more trouble than it's worth. If Cat 7 is often a trap for home users, then Cat 8 is the ultimate heavyweight that belongs in a very specific arena. This cable is a beast, capable of reaching speeds of 40 gigabits per second with a massive bandwidth of 2000 megahertz. But as you can see from the top half of our slide, its native environment is the high-density data center, not the living room. Here is the reality check. Even the fastest residential fiber plans in India rarely exceed 1 gigabit per second. Plugging a 40 gigabits per second pipe like Cat8 into a 1 gigabit per second internet tap won't make your water flow any faster. It is expensive overkill for a home setup. While it's impressive on paper, for 99% of us, the reliability of Cat6 or 6a is all the power we'll ever need. Choose your cable based on your actual hardware, not just the biggest number on the box. We've looked at everything from obsolete legacy wires to high-end enterprise cables. Now, let's bring it all together with a final recommendation based on your specific needs. If you are a basic user with a standard Wi-Fi 5 setup and a plan under 1 gigabit per second, Cat6a remains your most cost-effective choice for runs up to 100 meters. It's reliable, but it doesn't leave much room for the future. For the gamers, streamers, and work-from-home professionals, we land back in the sweet spot, Cat6. It handles 10 gigabits per second beautifully up to 55 meters, making it the perfect match for a Wi-Fi 6 router and a 1 gigabit per second plan. If you are doing a home renovation or have long-distance wiring over 50 meters, step up to Cat6a to ensure that 10 gigabits per second speed stays consistent across your entire property. And finally, we leave the Cat8 and specialized high-speed backbone links to the data centers and server rooms, where 40 gigabits per second is actually a requirement, not just a luxury. Choose the cable that matches your hardware today, but keep an eye on where you want your network to be tomorrow. We've spent a lot of time discussing how to optimize copper, but even the best Cat8 cable eventually hits a wall. To go faster and further, we have to break the copper ceiling. The problem with copper is physics. It transmits electrical signals that are inherently susceptible to electromagnetic interference, or EMI. As those electrons travel, the signal naturally weakens, a process we call attenuation. The solution? We stop using electrons and start using light. Fiber optics transmit data via photons, which produce no electromagnetic field and are completely immune to crosstalk and EMI. While electricity has a speed limit, light in glass travels at roughly 200,000 kilometers per second. This shift changes the conversation from megabits and gigabits to terabits. Fiber isn't just a faster wire. It's an entirely different medium that removes the distance and interference barriers that hold copper back. Let's look at how this technology actually works under the hood. To understand how we achieve those terabit speeds with light, we need to look at the remarkable engineering inside a single fiber strand. At the very center is the core. This is a hair-thin pathway made of ultra-pure glass or plastic, measuring between 9 and 62.5 microns, where the light actually travels. Surrounding it is the cladding, a reflective layer that acts like a mirror to keep the light trapped inside the core through a process called refraction. Because glass is fragile, we add multiple layers of protection. The buffer is the primary coating that guards against moisture and physical nicks. Then, we have the strength members, made of aramid yarn, better known as Kevlar, to prevent the cable from stretching or snapping during installation. Finally, everything is encased in the jacket, an outer protective sheath that is often color-coded so technicians can identify the signal type at a glance. It is this combination of fragile glass and rugged shielding that allows fiber to be both incredibly fast and remarkably durable. We know light naturally wants to travel in a perfectly straight line, but our networking cables need to bend around corners and through tight conduits. To solve this, fiber optics rely on a principle of physics called total internal reflection. As you can see in the diagram, when the light hits the boundary between the core and the cladding at a specific critical angle, the cladding blocks it from escaping. Instead of passing through, the cladding acts like a high-performance mirror, reflecting the light back into the core in a zigzag pattern. This allows the digital signal to navigate every bend and turn of the cable without losing its data to the outside world. It's this simple yet powerful interaction between the glass core and the reflective cladding that makes high-speed, long-distance communication possible. While every fiber strand uses that same reflective cladding, the size of the pipe inside makes all the difference in how the data actually travels. On one side, we have single mode, OS2. Its core is incredibly tiny, only about 9 microns wide. Because the pathway is so narrow, it requires laser precision to send a single straight beam of light over massive distances. On the other side, we have multi-mode, OM3, OM4. As you can see in the diagram, its core is much larger, ranging from 50 to 62.5 microns. This broader entry allows multiple modes or angles of light to travel simultaneously, making it easier and cheaper to use over shorter distances. To give you some perspective on just how small these technologies are, a single human hair is roughly 75 microns. We are effectively moving terabits of data through pathways significantly thinner than a strand of hair. Let's break down which one you should use for your specific network. Now that we've seen the difference in core sizes, you can probably guess why multimode is the go-to for localized networks. With its larger 50-micron core, think of multimode like bouncy balls in a wide hallway. Because the path is wide, we can use simpler light sources like LEDs or VCSELs to send multiple modes or rays of light simultaneously. However, this convenience comes with a trade-off called modal dispersion. Because some rays bounce more than others, the signals arrive at the end at slightly different times, which limits how far the signal can travel before it becomes blurry. Identified by its distinctive aqua or teal jacket, multimode is a high-bandwidth powerhouse for short-range sprints. It is the absolute standard for data centers, server rooms, and floor-to-floor building backbones, where you need massive speed without the massive distance. Now, let's contrast that wide hallway of multimode with the extreme precision of single-mode fiber. As we saw earlier, the core here is microscopic, just 9 microns of pure glass. This path is so narrow that light is physically constrained to a single, direct path. There is no bouncing and virtually no dispersion to worry about. Using high-power FP lasers at wavelengths like 1310 or 1550 nanometers, this technology acts like a sniper rifle of data. It fires a concentrated beam that can travel effectively infinite distances without losing its integrity. This is why single mode, easily identified by its yellow jacket, is the backbone of our global infrastructure. It powers long-haul ISP networks, undersea cables, and intercity links, capable of making single runs from 40 kilometers to well over 100 kilometers. Now that we've mastered the cables, let's look at the actual ports and power standards that make these connections come to life. We've seen that single mode is the undisputed marathon runner of networking. But in the real world, performance is always a balancing act with budget. The trade-off isn't actually in the glass itself. Single-mode cable is surprisingly inexpensive to manufacture. The cost lies in the electronics. Trying to hit a microscopic 9-micron target requires precision lasers and complex transceivers that are expensive, power-hungry, and generate a lot of heat. Multimode flips that script. While the cable itself is slightly more expensive to make because of the larger core, it can use cheap, mass-produced light sources like LEDs. For short runs under 300 meters, like those inside a single office or data center, the total system cost for multimode is significantly lower. So when you're designing a network, remember, use single mode to connect buildings or cities where precision is mandatory, but stick with multimode for internal connections to keep your infrastructure both fast and affordable. We've covered the physics and the costs, but when you are actually in the field, you won't have a microscope to measure those micron-sized cores. That is why the industry uses standardized color codes for instant identification. By simply looking at the color of the outer jacket, you can immediately tell what kind of data that cable is designed to carry. As you can see on our chart, yellow is the universal signal for single mode, OS2. If you see yellow, you're looking at a long-distance ISP feed. Orange represents legacy multi-mode, OM1/OM2. These are older standards you'll rarely see in new high-speed installations today. Aqua is the modern enterprise standard for 10 gigabits per second multi-mode, OM3, OM4. And Erica Violet, that distinctive purple, identifies the highest performance OM4 or OM5 wideband multi-mode, specifically built for the demands of modern data centers. Mastering these colors allows you to navigate a complex server room with confidence, ensuring you always plug the right speed into the right port. Now let's move forward and look at the actual ports and power standards that drive these connections. Now that we can identify our cables by color, let's look at the actual performance data that dictates which one you'll pull for your next project. This matrix highlights the defining difference between the two technologies. At a standard 1 gigabit per second, multi-mode is a solid performer up to 1,000 meters, but single mode is already in a different league, capable of reaching 100 kilometers on a single run. As we push the speed to 10 and 40 gigabits per second, notice the rapid drop-off for multi-mode due to that modal dispersion we discussed earlier. It falls from 300 meters down to just 150. Meanwhile, single mode maintains its incredible distance capabilities, even at extreme bandwidths. The takeaway is clear. While multi-mode is your high-speed, short-range sprinter, single mode is the only choice for the long haul. Understanding this matrix is the key to designing a network that doesn't just work today, but scales for tomorrow. With our media mastered, let's move on to the final part of our physical layer journey: multi-gigabit ports and PoE. You can have the most advanced single-mode marathon runner in the world, but it's useless if you can't plug it into your switch. On this slide, we see the evolution of fiber terminations. First, there's the LC, or Lucent connector. This is the modern, ubiquitous standard in enterprise switching, because its small form factor allows for high-density ports. Next is the SC, or subscriber connector, recognizable by its square, push-pull locking mechanism. You'll most commonly find these in fiber-to-the-home installations, or legacy data center gear. While the ST connector with its bayonet twist lock is largely a relic of the past, the MTP-MPO at the bottom is the future. It can terminate 12 or even 24 strands in a single plug, making those massive 40 and 100 gigabit backbones possible. That concludes our deep dive into media. Now let's step up the stack and look at the actual ports and power standards that drive these connections. We've seen the variety of cables and connectors available, but you might have noticed that most enterprise switches don't actually have dedicated fiber ports built in. Instead, they feature SFP slots, or small form factor pluggable slots. Think of this as a modular workflow that gives network engineers ultimate flexibility. It starts with the slot, an empty interface cage on your switch. To make it work, you insert the transceiver. This is a specialized module that converts light from the fiber into electrical data the switch can understand. Because these are swappable, you can choose a single-mode or multi-mode module depending on the run you need to make. Finally, the cable, usually with that LC connector we just discussed, plugs directly into the transceiver. This chameleon design means a single switch can support copper, multi-mode or single-mode connections all at once, simply by swapping the module to match the cable. This concludes our deep dive into media and interfaces. Now let's move on to the final part of the physical layer: power over Ethernet. We've seen how powerful and modular fiber systems can be, but they come with two critical rules that you can never ignore. Rule number 1 is the bend radius. It is easy to forget that you aren't working with flexible copper, you are working with glass. If you kink the cable, or bend it sharper than the curve of a tennis ball, you risk microbends that can shatter the core, or cause massive signal loss. Rule number 2 is about the invisible danger. You must never look directly into the end of a live fiber cable. While multi-mode can cause temporary blindness, single mode uses high-powered infrared lasers that are completely invisible to the naked eye. These lasers can instantly and permanently burn your retina before you even realize anything is wrong. Treat every fiber cable as if it is live and dangerous. Now that we know how to handle the media safely, let's move on to the actual ports and power standards driving these connections. We've covered everything from the physics of light to the dangers of the laser, so let's bring it all together with a final side-by-side look at our fiber options. 007 to 020, direct and analytical. On your left, a heavyweight champion for distance, single mode, OS2. With its tiny 9-micron core and high-powered laser source, it owns the long haul, capable of consistent runs from 40 to 100 kilometers. It is the undisputed king for WAN, campus backbones, and undersea links. 020 to 035, comparative and practical. On your right, the indoor specialist, multi-mode, OM3/4. Its much larger 50-micron core works with cheaper LED or VCSEL sources, which keeps your total system cost significantly lower. While its distance is limited to 300 to 500 meters, it is the perfect fit for LANs, office buildings, and server rooms. 035 to 045. Closing transition. Whether you need the precision of the marathon runner or the cost efficiency of the sprinter, understanding these specs ensures you pick the right tool for the job. Now let's leave the glass behind and move on to our final physical layer topics: multi-gigabit ports and PoE. We've seen how these cables move massive amounts of data, but one of the greatest innovations in modern networking is the ability to move energy through the exact same wire. This is Power over Ethernet, or PoE. As you can see in this technical cross-section, we are utilizing the existing twisted pair copper architecture of your Cat5e and Cat6 cables. Instead of needing a separate electrical outlet for every device, we use the unused wires in the bundle to deliver DC voltage. This allows a single cable to provide both the high-speed data connection and the electrical heart for the device. But this isn't just about plug-and-play electricity. To do this safely, we rely on complex IEEE 802.3 standards and negotiation protocols that ensure the switch only sends power if the device on the other end can handle it. Let's dive into these standards to see how PoE has evolved from powering simple desk phones to supporting high-power IoT systems. Now that we know who the players are, we need to understand the power gap, the difference between what a switch sends and what a device actually receives. On the left, we have the original IEEE 802.3 AF, simply known as PoE. This standard was designed for low-power devices like basic IP phones. While the switch injects 15.4 watts at the source, you'll notice the device only receives 12.95 watts. This difference is due to cable dissipation loss. As electricity travels through copper, it encounters resistance, which turns some of that power into heat before it ever reaches the endpoint. To handle more demanding hardware like PTZ cameras or Wi-Fi access points, we use IEEE 802.3 AAT, or PoE+. This nearly doubles the capacity, injecting 30 watts at the source to ensure at least 25.5 watts are available at the device. Understanding this loss is critical. You must always calculate your power budget based on the device requirement, not just the source output. Next, let's look at the ultra-high power standards that are pushing these limits even further. We've seen how these cables move massive amounts of data, but one of the greatest innovations in modern networking is the ability to move energy through the exact same wire. This is Power over Ethernet, or PoE. As you can see in this technical cross-section, we are utilizing the existing twisted pair copper architecture of your Cat5e and Cat6 cables. Instead of needing a separate electrical outlet for every device, we use the unused wires in the bundle to deliver DC voltage. This allows a single cable to provide both the high-speed data connection and the electrical heart for the device. But this isn't just about plug-and-play electricity. To do this safely, we rely on complex IEEE 802.3 standards and negotiation protocols that ensure the switch only sends power if the device on the other end can handle it. Let's dive into these standards to see how PoE has evolved, from powering simple desk phones to supporting high-power IoT systems. To understand how we safely deliver 54 volts of DC power over a data line, we need to look at the three main players in a PoE system. First, we have the PSC, or power sourcing equipment. This is typically your network switch. It acts as the brain and the battery of the operation, providing both the source of data and the electrical power. Next is the medium, which, as we've established, is your standard twisted pair Ethernet cable. Because PoE uses 54 volts DC, it can travel alongside your data without causing interference, provided your cabling meets the standards we've discussed. Finally, we have the PD, or powered device. This is the consumer of that power, such as the IP security camera shown here. The beauty of this architecture is that it eliminates the need for expensive electrical infrastructure at the endpoint. Now that we know who the players are, we need to understand the power gap, the difference between what a switch sends and what a device actually receives. On the left, we have the original IEEE 802.3AF, simply known as PoE. This standard was designed for low-power devices like basic IP phones. While the switch injects 15.4 watts at the source, you'll notice the device only receives 12.95 watts. This difference is due to cable dissipation loss. As electricity travels through copper, it encounters resistance, which turns some of that power into heat before it ever reaches the endpoint. To handle more demanding hardware like PTZ cameras or Wi-Fi access points, we use IEEE 802.3AT, or PoE+. This nearly doubles the capacity, injecting 30 watts at the source to ensure at least 25.5 watts are available at the device. Understanding this loss is critical. You must always calculate your power budget based on the device requirement, not just the source output. Next, let's look at the ultra-high power standards that are pushing these limits even further. Standard PoE served us well for phones and basic cameras, but as our devices got smarter, they also got hungrier for power. To meet this demand, engineers stopped using just 2 of the twisted pairs in the cable and started utilizing all 4. By effectively doubling the conductive cross-section of the wire, we can now move much higher currents without melting the insulation. This led to the development of Cisco UPoE, a proprietary technology that tripled the power available per interface. Today, this has evolved into the industry-wide IEEE 802.3BT standard, often called PoE++. Look at the progression on your screen. We've moved from 15 watts for legacy phones, up through 30 to 60 watts for UPoE cameras, and now all the way to 90 watts, with 802.3BT Type 4. This is enough to power not just cameras, but laptops, LED lighting systems, and even large digital displays. With the ability to deliver nearly 100 watts over a single data cable, the distinction between a network and electrical cable has officially disappeared. We've traveled from the basic desktop phone to high-power industrial appliances. This table represents the final cheat sheet for your power budget planning. Notice the evolution in twisted pair usage. Our legacy PoE 802.3AF and PoE Plus 802.3AT standards only utilize 2 pairs of the cable, delivering a maximum of 30 watts from the switch. But once we move into the 802.3BT era, our PoE++ and Type 4 standards, we shift to 4-pair usage. This allows us to jump from 60 watts all the way to 100 watts at the source. However, I want to draw your attention to the final column, power at device. Because of that electrical resistance we discussed, you must plan for a significant drop. For a 100-watt Type 4 source, your device may only receive between 71 and 90 watts. Whether you are installing a simple VoIP phone or a high-end industrial appliance, matching the right IEEE standard to your hardware is what ensures a stable, safe, and efficient network. We've seen how PoE can power a device, but as our Wi-Fi 6 access points started demanding more than 1 gigabit of data, we hit a major infrastructure wall. Standard 10 gigabit gear is expensive and often requires specialized cabling. To solve this, the industry developed multi-gigabit technology, specifically designed to squeeze more speed out of the copper cables you already have in your walls. By supporting the N-base-T standard, these ports can negotiate intermediate speeds of 2.5G and 5G. This allows you to upgrade your network speed for modern home and office demands without the massive cost of a full 10G enterprise overhaul. It is the perfect middle ground, giving you the target speeds needed for high-performance wireless and fast local storage while using existing reliable copper. This concludes our deep dive into the physical world of networking. We've covered a massive amount of ground today, transitioning from the physical wires in our walls to the invisible light pulses that power the internet. We started by comparing the sweet spot of copper Cat6 and 6A with the high-speed marathon runners of the fiber world. Whether it's the cost-effective short-range sprint of multi-mode or the 100-kilometer reach of single-mode, choosing the right glass is critical for your infrastructure. We also explored the bridge to the future with multi-gigabit, mGig ports, allowing us to hit 2.5 and 5 gigabit speeds on existing copper. And finally, we saw how PoE++ is transforming our data lines into high-capacity power lines for the next generation of IoT devices. Now that we've mastered the physical world of cables, light pulses, and power standards, it's time to look at the brain that coordinates it all. In our next lesson, we are diving into the OSI and TCP/IP models, effectively the universal maps of networking. We'll break down exactly why these models still matter for professional troubleshooting in 2026, keeping you ahead of the curve in a rapidly evolving field. We'll explain the 7 layers simply, moving from the raw bits you just learned about up to the actual applications you use every day. Most importantly, we'll demystify encapsulation and decapsulation, the process of how your data is enveloped and addressed as it travels across the globe. Get ready to move from the how of physical media to the why of logical communication. I'll see you in the next module.